This is CPE 133. This is essentially Chapter 7 in the Free Range Verilog Foundation Modeling book. And what we want to talk about in this chapter is mainly procedural blocks. And we are going to drive that discussion by implementing some decoders and providing a lot of support information. So, the disclaimer in this chapter is there is a lot of support information. So this is just information that you need to know one way or another to get up and coding in Verilog. Now, it's just a lot of information. It's a lot of information at the same time. It becomes second nature once you start using it. My suggestion is, go through this pretty fast, then try to actually implement some circuits, model some circuits, and then go back and read it again. So essentially, the issue is you're not going to learn Verilog by reading about it or listening to boring videos about it. You actually got to sit down and do it. So I encourage you not to get overly fixated on these videos. Go out and try some stuff. Okay, so the decoders are a standard digital module. I call them foundation modules. They're conceptually simple devices, but the implementations can become pretty complex. So because the implementations are complex, we don't even attempt to implement them or model them with data flow models. We go right to behavioral models. And that's why essentially the whole focus of this chapter is behavioral modeling, which is always blocks. So always blocks are the heart of behavioral modeling, and there's several statement types and assignment types that we need to talk about to get you up and going with always blocks. So the decoders in general, I classify them as two types, and that's generic decoders and standard decoders. As you can see from the Venn diagram, the standard decoders is just a special subset of a generic decoder. So decoders in general are simply lookup tables. So anytime you can define something like a function or whatever you want to define with a table, it's just super simple to translate that table into some Verilog construct, we'll say. So essentially, if you recall, that logic gates themselves are defined by truth tables. So this is a quick review. Behavioral modeling, we're going to use procedural blocks, namely always blocks for behavioral modeling. There's actually two types of procedural blocks. We are only going to use always blocks. And what we're going to do, generally speaking, is fill those always blocks with either assignment statements or procedural programming statements. So the procedural programming statements are the if statements, if else, and the case statements. We'll see examples of that later. And so when we do assignment inside always blocks, we'll say there's two types of assignments. You'll see this over and over again. We're not going to really go into it in depth in this chapter, but there's blocking assignments and non-blocking. And so we're modeling a decoder, which is a combinatorial circuit, so we're always going to use blocking assignments. Non-blocking assignments are for sequential circuits, which we get to later. So you gotta assign stuff in Verilog. We've seen wires before, and we use those in the continuous assignment statements. And what we're going to see is there's a new type of variable. Remember, wires are a net type, reg is a variable type. So when you assign something in an always block or a behavioral model or procedure block, it has to be to a reg. You can't assign something to a wire inside a procedural block, and you'll see that in the examples coming up. Okay, once again, I'm just going to plop that out there. We'll talk more about that when you actually are using sequential circuits. So quite often, this is some of the support materials. Quite often in Verilog, you need to represent integers in your models. So Verilog supports 4 different radixes or radii here, which is decimal, binary, octal, and hex. Essentially, I don't think I've ever used octal anytime ever, but the other ones I use quite often. You'll use them quite often. So this is the way you specify integers in Verilog. So essentially you can specify the size in bits. This is actually optional. You specify a radix, and then you have to specify the digits. So it's really, and most importantly, there's this little tick mark in there, and that's not optional. So the best thing to do is kind of look at a few examples on this one, and we'll crank through this. So for example, the first one up here, it's just the number 12. There's no radix specified, so it defaults to hexadecimal. Additionally, since there's no size specified, it defaults to 32 bits. So here, this is the value of 12. This is the binary value of 12 right there that it defaults to. And then there's going to be 28 zeros right here. So this is also hexadecimal. I'm using the tick notation here. The H stands for hexadecimal. I didn't specify the size, so once again it defaults to 32 bits. And here's the E right here, which is 1110, etc., etc. Here, right, what we have here is and actually have some. I'm specifying the size. It's 8 bits long, and it's the value of 34. And so what you could see is it's also a decimal number. So 34 is in decimal. So 34 is going to be 2 times 16 plus 2. So there's your 2 times 16, and there's your plus 2 standard hexadecimal format, and so on and on. So I don't want to go step through all these, but one of the nice things about Verilog is it lets you stick in this underline character to kind of separate values, and you can stick that in anywhere you want. It's actually ignored. So for example, this is this 8-bit value. I'm specifying it in binary, and there are my 8 binary bits. I stick this underscore in there just to make it more readable. And here is this value right here, which is equivalent to that value. So once again, I just know where the slide is, and I oftentimes forget how to do this stuff, but I know where to find it. And that's what I would expect of anyone learning this Verilog. So concatenating signals, there's oftentimes you need to create new signals from kind of an aggregate of other signals. So Verilog has a concatenation operator, which is these two curly braces. Once again, let's take a look at a few examples, and this is another classic thing where, I kind of am familiar with this, but typically I'll forget it, and I forget the syntax, and I know where to look it up, and so once again I encourage you to do the same. So looking at this thing, I have an always block down here, and I'm assigning signals in that always block. So these signals right here are defined or declared as reg types. That's one exciting thing about this slide. This is a big long slide. I'm only going to go through one of these examples here, and I'm going to go through this example right here. So this example is assigning a value to new sig 5. So here's new sig 5. If you look at it, it's 15 bits wide. Make that a 15 bits wide. And so what I'm going to do here is assign it 4 of these bits, and I'm going to assign it the B signal and the C signal. So this special notation here, what it says is take whatever A3 is. A3 is a part of this signal. Repeat it 4 times, which is this little signal here. Put that at the front, the leftmost of the variable. Then I'm going to add B. B is a 5-bit vector, and C here is a 6-bit vector. And so whatever B and C are, it's going to be tacked in there. So in order, so the leftmost 4 bits are these, the middle bits are these, the least significant bits are formed by the C variable. So all in all, this 4 bits plus 5 bits plus 6 bits is in fact 15 bits, which is what we want there. So essentially there's rules to how you assign these, and in case you don't match them. I actually don't really know those rules because I actually assign them exactly right, and I don't rely on the synthesizer filling in stuff for me. So we are at always block. So this is the general form of an always block right here, and what we have here is, you know, always with an ampersand, and then we have the sensitivity list. Scratch that out. I don't know what that says. What I'm trying to say here is, in the sensitivity list, you put all the input signals in that list. Now that's kind of a generic way of saying it, but we're going to be modeling decoders. Decoders are a combinatorial circuit. Put all the inputs in the sensitivity list. This is something kind of we'll once again readdress later, but for now, put all the input signals in there. There's a begin and an end statement, which delineates the body of the always block, and inside this always block we have statements, and we have three types of statements we can put in there. One is just a basic assignment statement, not a continuous assignment statement, but there's also an if these procedural programming statements, which is if else, and the case statements, and we'll see examples of that coming up. So let's crank through this thing. So here we go, procedural programming. We're almost there. Procedural programming statements, one is the if-else statement, and there's essentially there's two formats of it. We'll go through this in a second, but we are modeling combinatorial circuits. Therefore, our procedural programming statements, which is the if-else statements, it always has a catch-all. So both of these formats here always have an else statement. The else forms a catch-all. Now, when I'm modeling combinatorial circuits, they always, generally speaking, have to have a catch-all. So, for example, if this if didn't have an else, it would probably not be a combinatorial circuit. It would be some type of sequential circuit. But using an else, not always required, but you should do it because it provides a message to the human reading this that you're modeling a combinatorial circuit. So C, I'm sorry, this Verilog is very much like C. I don't need to put begin in the ends for these if and else clauses, but I usually do. It just makes it easier to read. If I don't put a begin and end in there, I can put only one statement in there, very much like C programming. If I put a begin and the end in there, I can put as many statements between associated with that if as possible. So once again, if you only got one statement associated with the if, you don't need to begin and the end. So the other procedural programming statement is the case statement. As just in a higher level language, case is a special case of if else. And the issue here is that this is the format down here. This is the expression that your testing will say, and these are the test cases. Okay, so if that expression tests to this case, this statement is executed, etc., etc. And so it's going to step through this list of these case items here until one of these statements evaluates as true. All right, and it's going to step through until one of them matches, and when it finds one that matches, it's going to execute the statement. If it never finds one that matches, it's going to take the default. Now, when it takes the default, that's essentially a catch-all. We're going to be modeling combinatorial circuits, so all of our statements are going to have some type of default in there. If it didn't have a default, it would not be a combinatorial circuit, most likely. Comments on that later too. So lastly here, there's procedural assignment statements, which we put inside always blocks, and there's two types. There's blocking assignments and non-blocking assignments. So this is actually kind of tricky. It's really a deep subject here. We're going to talk more about this later. For us, it's pretty easy to follow because we're modeling a combinatorial circuit, we are always going to use blocking statements. And essentially the difference between these two statements is one's an equal sign and one is a less than equal sign, which is not really a less than equal sign. It's kind of like an arrow pointing to the left. And we'll keep going on here. Yes, once again, very deep subject. We'll talk about more about this later. Okay, so we need, since we're going to use if statements in here, we need some equality operators. Verilog has a big list of equality operators. We're only going to use 2 in this chapter, which is the equivalent operator, equivalency, and the not equivalency. So it's the assignment operator is an equal, but the equivalent operator is 2 equals. So this is a super common mistake. Essentially, people will put 1 equal sign inside of an if statement. It's not going to be true. It's not going to work generally. It works sometimes if you get lucky, but that's something you don't want to do. So the condition inside these parentheses is going to evaluate as to be either true or false, and essentially it generates a 1-bit result, which is kind of most likely a Boolean, but I still like to think of it as a 1-bit result. Okay, so this is our first example. This video has already been long enough. I'm gonna end it here, and I'm gonna start the next video with this slide.